Our sun provides the energy for almost all life on Earth. Our sun provides the energy for almost all life on Earth. It is a constant, steady presence in our sky, a source of light and warmth. It is a constant, steady presence in our sky, a source of light and warmth. We organize our days and our years around its cycles. However, this familiar star is not entirely benign. It is a dynamic, sometimes violent, celestial body. Periodically, it releases immense bursts of energy and plasma into space. These are known as solar storms. Most are harmless, their energy deflected by our planet's magnetic shield. But what would happen if a truly massive solar storm, one of historic proportions, were to strike our modern, technology-dependent civilization directly? This is not a question of science fiction. It is a question of when, not if. The historical record provides a chilling precedent. In 1859, the most powerful geomagnetic storm ever recorded struck our planet. Named the Carrington Event, this solar superstorm induced electrical currents so strong that telegraph systems across North America and Europe failed. Some operators received electric shocks, and telegraph pylons threw sparks. The aurora borealis was visible as far south as the Caribbean. While it was a spectacular and disruptive event in the 19th century, its impact was limited by the technology of the era. If a storm of similar magnitude were to occur today, the consequences would be orders of magnitude more severe, cascading through every layer of our interconnected global society. Our world is woven together by a delicate web of technology. From the power grids that light our cities and run our industries, to the satellites that provide global communication and navigation, we depend on GPS for everything from aviation to agriculture. The internet, financial markets, and global supply chains all function because of a constant, stable flow of electricity and data. A Carrington-level event today would not just cause sparks on a telegraph wire. It would deliver a planetary-scale shock to this intricate technological infrastructure, with the potential to trigger a chain reaction of failures that could last for months, or even years. This exploration will examine the real-world consequences of such an event. We will begin by understanding the science behind solar storms and our planet's defenses. Then we will trace the immediate effects, from the moment the storm's energy impacts our magnetosphere through the initial hours of technological breakdown. Following this, we will analyze the system-wide impacts on our economy, infrastructure, and society. Finally, we will consider the long-term timeline for recovery and the critical lessons this scenario teaches us about our vulnerabilities and the importance of preparedness. Our journey is one of discovery, grounded in established science and the logical progression of cause and effect. The Sun, a star of average size, operates as a massive nuclear fusion reactor. Deep within its core, immense pressure and temperature fuse hydrogen atoms into helium, releasing vast amounts of energy. This energy radiates outward, powering the star and creating a complex system of magnetic fields that govern its behavior. These magnetic fields are not static. Twist, stretch, realign in a continuous, dynamic dance. When these magnetic field lines become overly stressed, they can snap and reconnect in a process known as magnetic reconnection. This event releases an enormous amount of stored energy in a very short time, manifesting as a solar flare, an intense burst of radiation, or a coronal mass ejection, known as a CME. A solar flare is a flash of high-energy radiation, primarily X-rays, and extreme ultraviolet light, which travels at the speed of light. It reaches Earth in just over 8 minutes, capable of causing immediate radio blackouts on the sunlit side of our planet by ionizing the upper atmosphere. A coronal mass ejection, on the other hand, is a far more substantial event. It is a massive eruption of magnetized plasma, a cloud of protons and electrons, blasted away from the sun's surface at incredible speeds, ranging from 250 to 3,000 kilometers per second. While a flare's immediate impact is electromagnetic radiation, a CME's threat comes from the direct collision of this billion-ton cloud of plasma with Earth's magnetic field. The frequency and intensity of these solar events are not random. They follow a predictable, albeit variable, pattern known as the solar cycle. This cycle lasts approximately 11 years, measured by the rise and fall of sunspot numbers on the sun's surface. Sunspots are cooler, darker areas where magnetic activity is particularly strong. The peak of the cycle, called the solar maximum, is characterized by a high number of sunspots and a significant increase in the frequency of solar flares and CMEs. Conversely, during the solar minimum, the sun is much quieter. Our ability to forecast these events is improving, but we typically only have hours to a few days of warning for a CME heading directly toward Earth. Historical observations provide crucial data on the potential magnitude of these storms. The Carrington Event of 1859 remains the benchmark for an extreme solar superstorm. More recently, in March 1989, a less intense storm collapsed the entire power grid of Quebec, Canada, in just 90 seconds, leaving millions without power for 9 hours. A near miss occurred in July 2012, when a Carrington-class CME erupted from the sun, but was not aimed at Earth. Had it occurred 1 week earlier, it would have resulted in a direct hit, with modern scientific analysis suggesting it could have caused unprecedented and long-lasting damage to our technological infrastructure. These events confirm that major solar storms are a recurring natural hazard. Our planet possesses a natural defense against the constant stream of charged particles from the sun, known as the solar wind, and more violent outbursts like CMEs. This defense is the magnetosphere, a vast magnetic field generated by the movement of molten iron in Earth's outer core. This field extends tens of thousands of kilometers into space, acting as a bubble that deflects the majority of incoming solar plasma. When a CME strikes, the magnetosphere is compressed on the side facing the sun, and stretched into a long tail on the night side. The interaction transfers immense energy into Earth's magnetic environment, triggering a geomagnetic storm. The most visible effect of this is the spectacular aurora, the northern lights, and the southern lights. This happens as charged particles are funneled along these field lines toward the poles, where they collide with atoms of oxygen and nitrogen in the upper atmosphere, causing them to glow. During a powerful geomagnetic storm, the auroral ovals expand dramatically, allowing these lights to be seen at much lower latitudes than usual, as was the case during the Carrington Event. The intensity of a geomagnetic storm is often measured using scales like the KP index, which quantifies disturbances in Earth's magnetic field on a scale from 0 to 9. A major storm would register as KP9. While the magnetosphere protects life on the surface from direct radiation, it cannot completely prevent the storm's energy from affecting our technology. The rapid fluctuation of Earth's magnetic field during a storm induces electrical currents in the ground. These are known as geomagnetically induced currents, or GICs. These currents seek the path of least resistance, which in our modern world is not the Earth's crust, but rather the long conductive networks we have built across it. Power transmission lines, oil and gas pipelines, and undersea communication cables. These man-made systems become unintentional antennas, collecting and channeling the GICs. The primary vulnerability lies within our high-voltage power grids. GICs are quasi-DC currents, meaning they flow in one direction for an extended period. Power grids, however, are designed to operate with alternating current. When GICs flow from transmission lines into the large transformers at electrical substations, they can cause a phenomenon called transformer saturation. This leads to severe overheating in a matter of minutes. The transformers, which are the backbone of the grid, can sustain permanent damage or be automatically taken offline by safety systems. If this happens simultaneously across a wide area, it can trigger a cascading failure and a widespread, long-duration blackout. The first sign of the superstorm's arrival is not the main cloud of plasma, but a powerful burst of X-rays and extreme ultraviolet radiation from the associated solar flare. Traveling at the speed of light, this electromagnetic pulse strikes the sunlit side of Earth just over 8 minutes after leaving the sun. Its primary impact is on the ionosphere, the upper layer of our atmosphere. The intense radiation dramatically increases the ionization of this layer, causing it to absorb high-frequency radio waves instead of reflecting them. The immediate result is a widespread radio blackout across the entire sunlit hemisphere, affecting long-distance aviation, maritime shipping, military communications, and amateur radio operators. This effect can persist for several hours, creating the first wave of systemic disruption. Following the initial flare, the storm's most damaging component arrives, the coronal mass ejection. This billion-ton cloud of energetic protons and electrons slams into Earth's magnetosphere, typically between 15 to 72 hours after the eruption. This collision drastically compresses the magnetic field, pushing the magnetopause down to dangerously low altitudes. Satellites in geosynchronous orbit, normally sheltered inside this bubble, can suddenly find themselves exposed to the full force of the solar wind and its energetic particles. These particles can cause significant damage to satellites' core systems, threatening the orbital infrastructure that underpins global communications and observation. Surfaces and internal components can accumulate an electrical charge, leading to electrostatic discharge, essentially a small lightning strike, which can short-circuit and permanently damage sensitive electronics. This is known as a single-event upset. High-energy protons can physically degrade solar panels, reducing their ability to generate electricity and shortening operational lifespan. In severe cases, the storm can confuse star trackers used for orientation, causing satellites to lose attitude control and tumble, rendering them useless until ground control can attempt recovery. The cumulative effect across constellations would be immediate and severe. Hundreds of satellites could experience simultaneous anomalies, overwhelming ground control stations that can only manage a few recoveries at a time. Many, especially older, less shielded satellites could be permanently lost. This leads to instant degradation of services we take for granted. GPS signals would become unreliable, weather forecasting models would lose critical data inputs, and satellite television and phone services would experience widespread outages. This initial phase of damage in space occurs before the most severe effects are even felt on the ground, setting the stage for a much larger, planet-wide disruption. As the geomagnetic storm rages in the upper atmosphere, its effects begin to manifest on the surface through a more insidious mechanism, geomagnetically induced currents, or GICs. The rapid and violent fluctuations of the planet's magnetic field induce powerful, low-frequency DC-like currents in the Earth's crust. These currents naturally seek out paths of least resistance. In the modern world, the most efficient conductors are not geological formations, but the vast, interconnected networks of high-voltage transmission lines that span continents. These long metal wires act as massive antennas, collecting the GICs and channeling them into the electrical grid's most vulnerable points, large power transformers at substations. Visual diagram: GICs flowing from the ground, up through a transformer's neutral and into high-voltage lines. The introduction of these quasi-DC currents into a system designed exclusively for alternating current is where the critical failure begins. The GICs push the transformer cores into a state known as half-cycle saturation. This means the magnetic core is saturated with magnetic flux, preventing it from functioning correctly during half of the AC cycle. This saturation causes the transformer's magnetic components to vibrate and generate extreme heat. The smooth sine wave of the AC power becomes distorted, creating harmonics that put further stress on the entire grid system, much like running a finely tuned engine with contaminated fuel. The most immediate and destructive consequence of this saturation is severe overheating. The internal windings of the transformer can heat up so rapidly that the oil begins to break down and boil. This process can cause irreversible damage to the transformer's insulation and windings in a matter of minutes. Protective relays, designed to detect such anomalies, would automatically trip to disconnect the overheating transformers from the grid to prevent a catastrophic explosion. While this is a necessary safety measure, the simultaneous tripping of hundreds of transformers across a wide geographic area is the trigger for a cascading grid collapse, leading to a regional or even continental blackout. In a Carrington-level event, this process would not be isolated to a single region. It would occur across multiple power grids at high latitudes, mid-latitudes, on the day side, and on the night side. Transformers would begin failing in rapid succession. Grid operators would be faced with an unprecedented crisis, attempting to stabilize a system that is being actively destabilized by an external force of nature. Vulnerability studies from organizations like the North American Electric Reliability Corporation suggest that a severe storm could damage or destroy over 300 large, extra-high-voltage transformers in the United States alone. This initial wave of hardware damage would be the primary cause of a blackout lasting not hours or days, but potentially weeks, months, or longer. The failure of the electrical grid is not an isolated event, it is the first domino in a long and complex chain reaction. Within minutes of the widespread blackout, secondary effects on other critical infrastructure begin to surface. One of the first systems to feel the impact would be water and wastewater management. Without power, water pressure would quickly fall, and taps would run dry. Sewage treatment plants would fail, and raw sewage could back up into streets and contaminate waterways. Hospitals and emergency services would switch to backup power systems, typically diesel generators. But these generators have a finite amount of fuel on site, and resupply depends on transportation and communication systems that are also failing. As hours become days, hospitals would face rationing power, straining their ability to care for patients. The food supply chain is profoundly dependent on electricity. From automated farms to processing plants and refrigerated transport, a prolonged blackout brings the system to a grinding halt. Perishable food would spoil. Supermarket shelves would empty quickly as panicked citizens buy up remaining goods. Without power for fuel pumps, trucks cannot refuel, severing the link between producers and consumers. Food shortages would appear within days. Transportation networks face paralyzing challenges. Traffic lights shut down, causing gridlock in urban areas. Electric rail systems, from subways to regional trains, cease to operate, stranding millions of commuters. Airports would be forced to ground flights as air traffic control systems, which depend on power, radar, and communication, go offline. The initial phase of the blackout immobilizes large segments of the population and the systems that move goods and people. In parallel with the collapse of the power grid, the storm's impact on satellites and ground infrastructure would trigger a comprehensive failure of modern communication systems. For remote and rural areas that depend exclusively on satellite connectivity, the internet would simply vanish. This loss of communication would severely hamper the ability of governments and emergency services to assess the scope of the disaster and coordinate a response. The global positioning system would become unreliable or entirely unavailable. The consequences would be immediate and far-reaching, affecting everything from aviation and shipping to logistics and emergency response. The internet's physical backbone is also vulnerable. The loss of power would shut down data centers, servers, and routers that direct internet traffic. More systemically, potential damage to the powered signal repeaters along undersea fiber optic cables could sever connections between continents, fracturing the internet itself. Financial markets, which depend on high-speed, cross-continental data, would be unable to operate. The combined effect would be a descent into a digital darkness. Without phones, internet, or television, information would travel only as fast as a person could carry it. Emergency broadcasts, if they could be transmitted, would only be receivable by those with battery-powered or hand-crank radios. This initial communications breakdown would be one of the most significant challenges in the first hours and days, compounding every other aspect of the crisis. The economic consequences of a Carrington-level event would be immediate and profound. The initial shutdown would bring financial markets to a complete halt. Businesses couldn't access capital or pay suppliers, couldn't meet payroll. A rapid liquidity crisis would erupt. As the blackout persists, damage shifts to a catastrophic breakdown of global supply chains. Modern manufacturing and retail run on just-in-time inventory. Without electricity, fuel, and GPS, the web of suppliers, manufacturers, and distributors begins to unravel. The direct repair costs would be staggering. A 2013 Lloyd's report estimated U.S. costs of $2.6 trillion, hundreds of custom power transformers, costing millions each, with a lead time of over a year to build, would need to be replaced. In the medium term, a severe global recession would be triggered. GDP would plummet, and mass unemployment would surge. Governments would face collapsing tax revenues and soaring demand for social support and emergency aid. Recovery would be slow, likely a decade or more for some sectors to return to pre-storm activity levels. The central challenge in recovery is physical damage to the grid's most critical components, the extra-high voltage transformers. These are not off-the-shelf items. They are massive, custom-built equipment, weighing hundreds of tons and requiring specialized transport to install. Global manufacturing capacity is limited. Manufacturing a single EHV transformer can take 12 to 24 months. If hundreds were destroyed simultaneously, nations would compete for limited manufacturing slots and transport resources. Even if new transformers exist, installation is slow and complex, requiring specialized cranes and highly skilled engineering teams. After a storm, with no power, limited fuel, and damaged transportation infrastructure, these operations become exponentially harder. Data centers, the heart of the internet, have backup generators, but they're designed to last only a few days. A prolonged blackout exhausts fuel reserves, and they go dark. This highlights the need for strategic reserves and hardened infrastructure. The long road to recovery proves resilience starts years before the disaster. The prolonged failure of fundamental services would place immense stress on the social fabric. In the initial days, Communities might rally together. However, as shortages of food, water, and medicine become acute, social cohesion would begin to erode. Fear and uncertainty, amplified by the lack of reliable information, could lead to panic buying, hoarding, and civil unrest. The impact would not be uniform. Higher latitude countries are significantly more vulnerable to grid collapse. This geographic disparity would create a complex geopolitical landscape, with potential disputes over scarce resources like fuel, food, and transformer manufacturing capacity. The event would demonstrate the profound fragility of our globalized system, forcing a re-evaluation of international interdependencies, and ultimately, the recovery process would necessitate a massive degree of international cooperation, making global collaboration not just an option, but a necessity. Our exploration of a modern Carrington-level event reveals a fundamental truth. Our greatest strengths, our global interconnectedness, our technological sophistication, our economic efficiency, are also the sources of our greatest vulnerabilities. We have constructed a complex, tightly coupled global system where a failure in one domain can trigger a cascading collapse across nearly every other aspect of society. The problem is not merely a power outage, it is the subsequent failure of water, food, communication, transportation, and financial systems that rely on that power. The outcome of such an event is not preordained to be catastrophic. Instead, it is a direct function of our awareness and preparedness. This scenario forces us to confront the fragility hidden beneath the surface of our daily lives. A solar superstorm simply pulls back the curtain, exposing the intricate machinery and its critical failure points. It demonstrates that resilience is not a passive quality, but an active pursuit. It requires us to look beyond immediate efficiency and short-term costs to invest in the robustness of the systems that sustain us. The central insight gained is that while the sun's fury is beyond our control, the consequences on the ground are not. The difference between a manageable crisis and a multi-year catastrophe lies in foresight, planning, and investment. The question it leaves us with is not whether we can prevent the storm, but whether we have the will to prepare for its inevitable arrival and mitigate its impact. The path forward is not one of dismantling our technological society, but of making it more robust. The solutions are known, practical, and achievable. Equally important is improving our ability to forecast and respond to space weather. With an accurate forecast, operators can take preventative measures. Beyond technological fixes, building resilience requires comprehensive contingency planning and a culture of preparedness from the individual level up to the national level. This is not about preparing for an apocalypse, but about responsible stewardship of the technological world we have created. The challenge calls for foresight, international cooperation, and a commitment to a future that is not just efficient, but enduring. What scenario should we explore next?